Welcome everyone to the manufacturer's latest webinar, Model-Based Systems Engineering in Real Life. My name is Nick Peters. I'm editorial director here at the manufacturer, and I will be your host today. Thank you so much for joining us. I'm delighted to introduce Andreas Korf, one of PTC's experts in model-based systems engineering, or MBSE for short. Andreas will be sharing his real-world experiences during this webcast. Also joining us is Dr. Zingel. Christian is a specialist systems engineer at test systems manufacturer AVL. Now, before we get started, we just have a couple of housekeeping points. If you've got any questions throughout the webinar, please use the Q&A button at the bottom, Q&A button, I beg your pardon, on the bottom of your screen, and we'll get to as many of the questions as we can at the end of the presentation. And you'll be seeing some quite detailed diagrams. I suggest you view this presentation in full screen. It should start in full screen, but if at any time you exit, you can click the Enter Full Screen button at the top right, which you'll see just above the presentation. After the webinar, we'll be sending all registrants a copy of the presentation, including the slides, along with our contact details. So please do get in touch if there's anything more you want to know about any of the issues raised. Right. Today's webinar is focused on model-based systems engineering and how it can be applied in real life. As products and product lines grow in complexity, it becomes increasingly difficult to create and communicate design ideas that can be easily understood, pardon me, and agreed by all stakeholders. That's why manufacturing leaders are increasingly adopting model-based systems engineering techniques that unify all stakeholders through a common visual language and structured engineering approach. This shift towards MBSE is why we've partnered with PTC to bring you this webinar to help guide you on how best to apply MBSE at your business. I'm now going to pass you over to Andreas Korf from PTC to let you know more about how you can benefit from model-based systems engineering. Over to you, Andreas.
Thanks a lot. Yeah, it's my pleasure to bring you a little bit, let's say, insights on model-based systems engineering, and also to talk about how this is helping a lot of our customers in order to getting the right questions and the right answers as soon as possible. I'm also extremely happy that Christian Zingel agreed on showing their insights, right? The details from AVL. Christian, do you want to introduce yourself, please?
Yeah, for sure. Thank you, Andreas. So hello from my side. My name is Christian Zingel. As already introduced, I'm a specialist for systems engineering at AVL. And AVL is a manufacturer for test systems and instrumentation systems. And I am responsible for the development of new processes and new methodologies all around MBSE at AVL, and also afflicted with interconnection to requirements engineering. Thank you.
Okay, great, thanks. Yeah, and may I also introduce myself? I'm Andreas Korf. I'm at PTC, responsible for business and market development in the area of MBSE for the EMEA region. Before this, I was also product manager for the tool which we are currently seeing at Zingel, and I'm doing systems and software engineering now for a little bit less than 26 years. Within the object management group, that's the organization which who's developing languages like UML and SysML. I'm also part of the revision task force for SysML. So I hope I can bring you, let's say, all the different perspectives from languages, tools, processes, and methods, plus, of course, the competencies needed here into this presentation. So our presentation scope is, first of all, to talk about collaborative MBSE. That means that this is not something for a few specialists, but it involves everyone who's part of the development and servicing team of a complex systems. And I brought some examples with me. First of all, of course, the AVL example, and Christian will present this. And then also BMW in a specific different spot about functional safety. Then I'd like to talk about the different system architectures and modular MBSE to design connected systems and MBSE to supply chains. The examples I will mention here is a German tier 1, tier 2 company. I'm not allowed to mention the name here, but of course we can talk about the general approach. All our systems are developed in product lines. So I'll bring the model-based system product line engineering also as an example from Alstom. Then Internet of Things, all of these type of connectivity and what to do in this area for system and software design. Another example from an aero engine manufacturer. And then product functionality simulation and improvement, where I have example for model-based specifications from the German rail infrastructure called DB Netz AG. And it should not be a kind of, let's say, walkthrough in the area of this is an example, this is another not connected example, and so on. I'd like to draw a red line through the topic of MBSE, which we could then follow. So we have defined 7 pillars to understand and also to use MBSE. And all of these pillars will be covered here in our presentation. First of all, how can we connect the different disciplines, mechanical engineering, software engineering, hardware engineering, the customers, the product management coherently? And so systems engineering will help us in this area. Then how can we define and our collaboration through the different levels of systems in our system architecture? What is the best common language? And is there something available? So we will talk about SysML. So there is a common language available and it is broadly used. The fourth pillar is about, let's say, that systems engineering has changed its attitude from the few experts dealing with the whole system, doing a document-based process, writing requirements and so on, to a completely different approach. Then how we can deal with product lines and how to deal with connectivity. And the last pillar is about, let's say, talk about modeling per se. Modeling is always useful, often necessary, but never an end in itself. So if you consider modeling of yet another burden to do in your engineering process, that's not the case. It will shift the paradigm a bit of how to work together and how to work, but it's not a kind of extra burden to be done in parallel. Okay, right, let's jump into the pillar 1, the systems engineering connects disciplines. When you see how the different disciplines are working currently, if you have a document-based process, they have their own silos and they are working together just at the very end where it is about integration of the different disciplines artifacts. So with using models, we are able to really collaborate in the right way, and also to work around to define as formal as possible, not as, let's say, as formal as needed, not as possible, in a pragmatic way, how to define models. If you write something down as a textual requirement, this could be also seen as a kind of model element. However, it is not formal. And if you want to get agreement from the complete team, it's good not only to define a glossary or requirements in a textual way, but then also to interlink these elements together. In an example here, we could see that, for instance, with an BMW developing nice cars, they have to follow safety critical rules defined in the ISO 26262, and during or within the norm, it is mandatory for certain criticality levels to use semi-formal methods. UML is written down as an example. So instead of doing this, they are really defining a system architecture as a basis to do functional safety analysis and functional safety architecture for their systems in chassis and powertrain. Within the INCOSE, that's the International Council on Systems Engineering, a worldwide group of systems engineering people, there is the vision of 2025, where systems engineering, which has a history of decades, also moves directly using models. So building up more formal approaches. It's even that defined that they'd like to get rid of the term model-based, because it's obvious that systems engineering will use models. In order to support this, a modeling tool chain would get some requirements in this area. So it's not my model, and many of them, but our model. Modeling UML or SysML is also not just drawing diagrams. It's the task of the modeling tool to bring all of these together in a good, complete, and errorless model dictionary. And not only the visualization and the diagrams are important. The other need is that you have to understand that it's not only the model, it's also not all the other development artifacts like CAD drawings, PLM, bill of materials, or requirements documents. It's need to bring everything together in a kind of federated single source of truth, with the modeling as the man in the middle. When you look into the definitions, for instance, from modeling languages like SysML, you could often see that this is quite a broad range of possibilities. So it is often seen as very, very complicated. However, a language like SysML is like any other language. It can offer you certain terminologies and grammar and information and notational possibilities, but you do not need to use all aspects of a language. So it is also needed to look into the different roles in this development team and to offer exactly the information, but also the modeling options you would need. So if we look into a modeling tool, PTC Integrity Modeler in this case, we have, first of all, I hope it's not too small to see this, we have a little example that's a model called PTC Automotive Example, and within the model I could go into a specific context where we could see there is a context of a car, for instance, a structure where we can have a look at. So we could have the elements relevant for powertrain, or we could have a kind of contextual information around what type of information is needed for defining the extended vehicle context, due to the fact that cars are always interconnected right now. So my vehicle is just a part of an extended context where I could use smartphones, and they have different operating systems I have to consider when I'm writing apps to connect with my car. So you can see that although these are just drawings, we are also able to, to get the same information from just a website in order to be able to comment on these things within requirements, for instance, or to have an insight in the different architectural elements. In addition, there are possibilities out to say, which is needed, I'd like to be able, for instance, only to model use cases. So all of a sudden, things are filtered out, and I can go into the different areas and just have the use case views, and other views are just filtered out. So I can directly concentrate on these things. There is something which is quite difficult to explain if you have one user with one model, but the important thing is also modeling tools like PTC Integrity Modeler are able to work in teams to have a multi-user approach without the need to check in, check out our stuff. It's like a booking system where I can get views on it, make a change, and these changes are immediately seen for all the other users. Okay, good. The next pillar is about collaboration through system architecture. The word system is heavily overused. When you are talking about what is a system with different people, you will see that there are a lot of ideas. So the system could be the traffic, the system could be the car, the system could be the factory producing the car, and so on and so on. So it is important to define the different contexts where I'd like to create a system and system architectures. In the area of models and model-based development, you will also very often find other approaches like functional models. And these functional models are really good when it comes down to the definition of, let's say, controllers, and very often they also have quite good possibilities to get device code or embedded code directly generated from these functional models. However, when it comes to reusability, they lack the possibility to define a model in an object-oriented way, which means a system is always a network of connected elements. This is derived from object-oriented languages, which influence the UML, the Unified Modeling Language, which also influence the SysML, because the SysML is just a kind of systems engineering dialect of the UML. So thinking in trees like bill of materials or other trees is a good thing, but you always need to consider them as filters of all perspectives. Everything is a network of things, and that's a very natural way of thinking. The requirements for a modeling toolchain is to keep type definition and type usage separate, to support abstractions and compositions as well as inheritance, and also to think about a model and model concept. An example in this area was this tier 1 manufacturer in Germany who wants to, let's say, grow their capabilities from producing mechanical products to a real systems provider. And it took them a bit to understand that all of their systems, when you're introducing functional architectures, when you're introducing use cases, the links to requirements, the different level of contexts, that all of this is needed in order to broaden their way and to integrate the hardware and specifically the software perspectives into their, let's say, mechanical world. But they are on a good track, and they are currently also developing highly sophisticated, quite complex systems in the area of electrical cars, for instance. So when we have a short look into our model again, we could have a look at an example we have created to introduce SysML. In COSI does not state the SysML has 9 diagram types and so on and so on. It really defines that we have different, the 4 different, they also talk about pillars of SysML, and all of these pillars are covering a whole concept of a holistic systems model. Okay, let me see why I have some problems here in order to get this thing up working. In the meantime, I could also think about introducing this here. Okay, good. As we have seen here, this is a system structural view in a so-called block definition diagram. There are other diagrams like use case diagrams, which are helping us in the area. Okay, my modeler didn't leave me alone, so that's good. I just have to get rid of the use case modeling only because I want to show you a little bit more of these things. So, okay. Good. Okay. I'm currently having a little bit of okay, adding derived roles. Okay, here we are. We have the system structure. Very often when you ask people where do we start with a SysML entry point, very often they say, well, we have requirements. But as in most cases, our system has to be found in, let's say, the context of other systems. It is much better to define the context up front. Do you agree, Christian, in this area? Do you also use system structure as the first view here?
Yes, in context of modeling the system environment, of course, we start up with identifying the interacting neighbor systems, and that in fact means our system is a black box. And we start up with identifying the other systems, also the human actors, and start up modeling with that in a block definition diagram, or also maybe a use case diagram, depending on the context. But that is true, yeah.
Yeah, exactly. So I see. Currently, my user roles are okay. It's currently filtering out these things. Let me just take this one. Of course, requirements are important, and requirements will also, coming from requirements management tools, they can be linked and synchronized within the model. Then you have also the system behavior. So for instance, you can discuss use cases with your customer, with your stakeholders. And it's very important to have here also, let's say, more graphical, attractive ways in a way. Use cases are quite textual focused, so we need to formalize them. So sequence diagrams are very helpful also to say what's the right scenario for all of these. Then you have activity diagrams and also state diagrams to describe behavior. Within the system structure, we also define the interconnection of these things, both from a system design for structural elements as well for functions. And we could also then add a fourth view, which is the parametric view, which brings in the physics in so-called constraint blocks. Okay, so let's go ahead with the examples here. Pillar 3 is the use of a common language. And it seems that SysML is there with the right information, the right possibilities of a language at the right time. So with the growing complexity and of things, but also the need to be compliant with norms like safety criticality. SysML is the common language, modeling language on system level. It can be adapted through lightweight extensions. So as the language does not impose a methodology, we have to define an agreed methodology, and we can change the language slightly in order to help introducing this methodology, but also to contain that the model can contain domain-specific information. SysML can also be used in parallel with other UML-based profiles within one model. So we have an example of another tier 1 supplier in automotive in Germany who is using SysML plus UML. So we have the systems view, the software view, plus AutoSAR, which is a software architecture language, which can be also described with a UML profile. And they bring everything together within one model, and they are generating embedded code as well as AutoSAR definitions interlinked with their requirements. So there are slight requirements on a modeling toolchain here as well. So you have to tweak the language and tweak the meta types using SysML. So you are not always see that there is, in fact, it's a stereotype UML object we are currently using. So if you see a requirement, then it's not good to see there isn't a default implementation language as Java, because this has nothing to do with SysML requirements or SysML blocks. The tool also needs to behave differently due to the profiles in use. We are calling this ergonomic profile. And we also need to map external information, and the profiles need to affect this mapping to external things like requirements or structural elements or code. The example I have here, in addition to what Christian will tell you later, is the so-called BMW SMART methodology. SMART stands for System Modeling, Architecture, Design, and Test. And it introduces functional safety in different levels. So they have very abstract items of consideration. I'd like to drive autonomously as a development goal. What needs to develop? And they are using SysML as well as elements from their SMART profile. Then they have an abstract concept, so they do not directly jump into the fact let's use a canvas here. So a solution-oriented, how should it work? Then a concrete concept, who is going to do what and how it will be implemented, and then the realization, how will the implementation look in detail. So they have everything in one model. They are using Modeler due to the adaptability, the multi-user support, and the interfaces into their existing toolchain. And it looks like this. So they have different traceability areas, which is needed for the compliance to ISO 26262. If you are coming from other means, the 61508 for functional safety in generic terms, or if you have rail norms like Selenic norms, they are also looking very, very similar. So it's a specific automotive example, but it works quite well. You have traces, you have derived requirements, you have status filings. All of these type of things are there in one model. So they consider their model to be their single source of truth, although this is linked with other domains. And all of the conceptual and creativity work is done in the model. And this slide is directly taken from BMW, so it is in German. So you have the testers, you have the functional safety people, you have the function developer, and you have the software developer. And they are all working within one model, but having their own perspectives. And when, for instance, somebody introduces a new functional safety concept, this has to be related with system requirements and views from the function developer, and they can all work together. I think you have the similar approach, Christian, as well, to have different roles and working together within model, correct?
Yeah, we do. In fact, we don't have those roles exactly, but we also define different roles working or interacting with system models. Sorry, and of course, we use the model as single source of truth for a particular context. Yeah, that's true.
Okay. Very good. Perfect. There are other examples, like, for instance, the SysML requirement subtypes, which are defined in exactly the same way to say, if you have the need to talk about functional requirements, design constraints, and stuff like this, all of this is defined in a so-called non-normative area of the SysML language, and it is exactly described in how to tweak the SysML language accordingly. Very often, systems engineering is seen as you need to have the overall picture of the complete system. That's true, but everyone should share this complete picture. So it's not only for the experts. So the system model can be seen as the man in the middle, and everyone is getting information and putting information in the model. Models are not just modeled, but also transformed, read, reviewed, released, annotated, changed, reused, and so on. And all of this is done based on, let's say, the concepts of connected elements, as I said, within the model. That means that when you need to see who has done what and who's responsible for what and what things I need to have as access rights, you need to have all of these things included. So you need to have a model compatible config management, access rights management, and you need to have different access to model information. For instance, automatic verification and reviews, which we have, a web access for read-only information, user roles, programmatic access in order to write your own analysis, for instance, and also link and sync between different models or between the model and other artifacts. An example of how to introduce models without exposing the models is the Deutsche Bahn. They were confronted with the fact that their textual specifications were not enough in order to ensure that all of the things like interlocking systems or light signals or any other areas are working together. So the interfaces and the interface definition was key. So they introduced a methodology to model their specification, and that's a lot of things concerning structural, but also state-based behavior. And so they can introduce the domain experts and say, could you please test, for instance, the connection between an interlocking system to a light signal with all of their specific types of signals, and it's very domain specific. And could you please log what you are doing, and we will see if this is correct or not correct with our model. So in order to validate the model, they can auto-generate a complete behavioral element using modular SISIM, that's system level validation, and ask someone to validate behavior even without knowing that this is in the model. And then they take this into their supplier's hands as a specification, and they can ensure that the implementation has to be compliant to the model instead of being compliant to written text. Another example of the introducing models here as well is the digital product traceability. So for instance, to be able to interlink the model and having model simulations connected with IoT systems which we have done with a street scooter, and we are currently doing with another electrical car manufacturer called Ego. You could directly generate device code, which we have done, for instance, in the connection with Schneider Electric, and we can push the model structure into our PLM systems in order to have the PLM experts reusing the structural views within the model. Pillar 5 is that, if you have a system, this system is always similar to other systems you're developing in parallel or in sequential area, depending on what you are producing, if it's engineering to order, or if it's really product engineering. So we need to connect product line engineering with system models. At PTC, we call this MBPLE, so model-based product line engineering. And we have an addition to our modeling notations called OVM, orthogonal variability model. This is defined and used in a norm in the ISO 26550. That's the norm about a reference model for product line engineering and management. You need to have a direct link between these variants and model artifacts, and also to generate product models directly from product family models. The previous type of thinking is to have several models and to clone and own what's similar within these models. That's quite okay when you have 2 or 3 things, but more and more products are included within a product family. So it's much better to take one product family model and to use it. Another example from the rail business is, for instance, a rail tier 1 supplier making rail brakes, and they are heavily changing their way of working using product family models. Alstom, producing trains, they realized that metro systems, for instance, are quite similar if they are in Jerusalem or if they are in Russia or in Brazil. But of course, they are also different. And instead of, let's say, having all these, again, silos of different products, they are working with a product family and can also generate product models directly from product family models. I have a little example for this. So currently looking for a model here. So it's the feature tree audio example. I will just create a new version for this in order to have a full access to a product family model. Okay. This is about an audio system where we have, for instance, use cases where we say we'd like to listen to radio, we'd like to have DAB, for instance, we'd like to play audio files, we'd like to use the phone in the car as well, and having other things like monitor power. And you see all of these fancy little variants here. They are interlinked with the model elements directly, and they are a part of our variability model. So the variability model in OVM is directly included in my product family model. This is currently shown as a tree, and maybe you have heard of feature trees and things like this. You do not need to have feature trees in OVM, but you can, of course, use a tree structure. This was developed for a customer who wanted to have trees as well, because they were directly, let's say, thinking in variability trees. And if you have this, you can make decisions on things. For instance, you could say, I'd like to create a very simple radio, just using an external tool for this, but internally could be also used here as well. So my audio examples could say, I do not need a hands-free kit. I also do not need to listen to MP3s. I just like to use radios. And you see then the only option available at which I could choose is I'd like to, let's say, whether or not to use DAB. And if I've done this, I can just create a product model from my decisions and the product family model. This is a kind of branch of the product family model, which I can then use for analysis or generation parts. Okay. Good. Okay. Perfect. And I can open this up. Modeler. It's called very simple radio here, in fact. Okay. And when we are now looking into our system, we can only listen to radio, but all the other things which are common to all other elements, they are there as well. As well as, for instance, functionality, function trees, or structural elements. Okay. This is heavily used with customers like Alstom, for instance. Good. Connectivity needs the system view. Another example here, when you are talking about Industry 4.0 or you are talking about any other IoT things, because it's important to see what is the system or how does my system of system work. And if I'm doing this and also abstract away the possibilities, we have them in the products as well as the development and usage concepts. So we can use exactly the same ideas and technologies to connect development artifacts as well as connected systems. And if I'm doing so, I can think about new business models with my abstract system level. There is a good example for this aero engine manufacturer who stops selling aero engines, but instead selling thrust or power by the hour, because they introduced all the other maintenance, servicing, and other things around this system within a system called airplane, within a system called air traffic also. So they are creating a win-win situation with the airlines, because they can ensure that if their system, their aero engine states, I need help, I need a spare part, then this is in parallel sent to their organization. And a spare part might wait for the aircraft, which is then landing at a certain place. In order to do so, we need to have the same connectivity approaches and techniques for the connected systems, and possibly automate generation of, for instance, device code, as well as for the connected development artifacts. At PTC, we are doing so. So our ThingWorx technology is also used to connect our different PLM, ALM, and modeling tool chains. It's based on standards like OSLC, REST, and also reusable asset specification, another standard from OMG. Good. So as an example, from Modeler, we could have variabilities or variable structural elements to wind chill, but our traceability is using the same technology like the aero engine manufacturer, for instance. Okay, the last pillar is about modeling itself. So if you say, let's start drawing diagrams, that's, let's say, a nice intro, but models are more than just diagrams. Diagrams are just filtered views on my model. So we need to really think about a transformation from document-based to model-based systems engineering approaches. It's a general trend because formalizing things is a general trend. If you do not formalize, then the discussion about what is right, what is wrong, if something is missing, and so on, will only come at the very end when you need a decision. And using models will help you to ask the right questions at the right time. Model-based specifications, as an example, are putting this a little bit further out because you have also the possibility to express requirements in a model, so a more formal requirements perspective. It's not easy to ask someone who is writing requirements for our system to be a little bit more precise. However, it is really helpful, and languages like SysML will definitely help you in order to describe things in the problem domain. And if you do so, you could see that statements like within BMW saying our common knowledge is based on the model, or a partner from us in Switzerland says, well, we have modeled our whole company, so our common knowledge base is in the model. There is another side effect on this. Working on one common model will introduce continuous engineering and putting information into the model as the normal way of working. I do not need to check out or check in things at the very early time. I have all the control mechanisms to say, okay, I need to control who has done what and why later on, but it should not be the case in all engineering phases. From Alstom, we got a nice statement in this area that in order to find out the answer of a specific question, you can kindly play or work with a model. So you need to have model exchange in different development phases. You need to respect intellectual property concerns, which could be helped with OMG RAS because it defines interfaces for reusable assets. You need to version models, define the product status, but be open then to change the last version. You need bridges and all the other development areas, ALM, requirements management, product lifecycle management. And you also need to think in incremental steps in order to transform from textual systems engineering to the use of connected system models. There's not just one big switch to do this. Just look for the things which are, let's say, low-hanging fruits in order to get early results. A customer of us, Safran, did this, talking about their systems engineering process and how to change it. And they are using a tool like Process Director, PTC Integrity Process Director, to model their process and to introduce the process before going into the system modeling. Okay, so now it's up to you. I'm really eager to see how you are using something what is called Lean MBSE, Christian.
Yeah, I just give you a brief introduction in one of our use cases, how we adopted MBSE as a methodology that really improved our work efficiency. The example I brought to you is from the context of customer projects we operate. So we, as I said at the beginning, are a test system manufacturer. So we supply OEMs with test systems. And we often have the challenge that they submit requests for proposals and just give a time of a few weeks to receive adequate offers for right system solutions. So we have the need that our system solution we offer must meet the customer needs, of course, firstly. Then, of course, the price must be attractive for the customer, but still profitable for AVL. And that requires, again, that we have a reliable and cost-efficient calculation of what possibly might be occurring development work or application effort we have to do to supply the right solution. And that means we need to efficiently align with the portfolio strategy on the one hand and product management, of course, towards the decision on the implementation of which new function customer might want to have is implemented in a standard product, because we think that could also be reused for other customers, or we have to decide on a more easy customer specific implementation what does not have that comprehensive testing effort, of course. So what we basically do for that, or have to do for that, is on the first hand we have to clarify the why. So that means we have to analyze what are the customer needs, what does he want to do with the test system? Secondly, we need to synthesize out of that needs the functionality and the properties of our system that satisfies these needs. So we have to clarify the how we do those use cases. And finally, we have to derive the best system configuration or solution. That means what will we deliver to the customer? And for doing those tasks, we have several requirements. I've listed some of them. So the description of the right solution and the according needs have to be consistent. It needs to be analyzable, what we document there. We want to reuse it for other customers, maybe that have similar needs. And we need an understandable documentation of all aspects to improve the communication in sometimes very large project teams. So what you see in the next slide is our concept we developed for this purpose. On the one hand, we have established a so-called instrumentation and test system structure. This is a modular structure for our different types of test beds. This small picture just shows, let's say, containers where we classify different product solutions in so that we can see which functionality, for instance, fuel consumption measurement, does the customer need to have, and which according solution do we offer for that. Secondly, we have defined standard interfaces between these modules in this modular structure and the standard functions they have, so that we can assign the product functionality and assign the product interfaces to the modules to be sure that our products fit well in the modular structure and interoperates well. We covered those aspects in using SysML for documentation and describing all these information. And you can see this small picture in the middle representing a little structure. We see more later on. But what I want to show you first is what we expect to have as benefits for the different target groups. On the one hand, we have the product management. Product management needs to obtain an overview which public interfaces of their products are interacting with other systems, and not also other systems from AVL, but especially also third-party systems, for instance. So secondly, then they need to have a clear mapping from the system use cases. That means the use cases of the entire test bed is how these use cases are interacting with the product functions, or in other words, how the product functions contribute to the system use cases. So that brings the context for the product functions. And they also need an information basis, and they gather this from the model, for the definition of standard conform interfaces. So that means if we develop our own technologies beside existing standards in the world, we define them also in such a model to be sure that the interaction of the products is always consistent and working well. So Test Center, that is our department for system integration testing, they need information about which functions and interfaces they have to test. And when products are developed well, then they can be applied in the customer projects for providing the system solutions. And there we expect benefits for the operations team that assembles the system solution and communicates with the customer in that case, and also for the service, that they obtain transparency of the dependencies between the interfaces and functions of the different applied product and systems, so the resulting system configurations. And they need to obtain a clear, or they gather a clear communication regarding issues that can appear regarding the functionality or the interfaces of the products. That is especially true for the service. When we do the commissioning of the system and do the on-site testing, they can clearly communicate which function is affected, which interface is affected. And hence the product teams also get transparency about where are their products applied, what functionality from the technical side is needed to satisfy the system functionality, and therefore they can derive clear requirements. So what you see on the last slide is, this slide, thank you, is just a small example to visualize this a little bit. On the one hand, you have the subsystem use cases. Those are the use cases derived from the system use cases. There we can model the different subsystem functionality and the interacting systems, and on the other hand the interfaces, where we model how the subsystems are interconnected to actors and also other subsystems. And this helps us as a SysML model that collects all this information to reference into the different participating product development teams, but also the operations team, to improve the communication using those clear diagrammatic or graphical views and interlinking that to the product specific detailed documentation. And this is basically done by referencing. So it means when the product teams work on other tools like shown, for instance, like Confluence, a wiki system, or just use PDF, Word, Excel, and so on, they can use hyperlinks or maybe use web interface possibilities to access on the central model, that lean core model, to gather the information of the interacting neighbor systems or the interaction functions they have there. So this is just a brief overview so far.
Yeah. What I really like is that your methodology is also a pattern which could be reused also for manufacturing, because it's always the same. You have certain development groups developing elements with capabilities, and within the different project teams, they are reusing these things, and everyone has to have an overview about what is available and how it is used and reused.
Exactly, yes.
Okay, here is another view on the MBSE, ALM, and PLM interoperability, which we have created, very similar from what you showed, Christian. So you have different perspectives in the model, and you have the links to other areas as well. For instance, requirements in an ALM tool chain, you have bill of material structures, including variability, all being interlinked with these specific views within one model. So the model is really the man in the middle. Okay, so that concludes what we said. Yeah, we have some time for some questions, and as you see, you can model everything. So even our questions and answer slide is modeled in a sequence diagram, stating when you have questions, we will try to answer them now. If you have other questions later on, then you will also see our mail details, so you could also send them up to us. So, okay, good. You have some instant questions which we could answer.
I would have the question regarding the product line engineering. In how far you can also connect multiple models. So let's say models and models for modeling different variants of different product lines, which might also reuse single components across product lines. So do you have the possibility to not just make one product family model, but rather also to connect multiple product family models in any extent?
Yeah, you can do this. The solution is in the language which I've mentioned called RAS, Reusable Asset Specification. It defines the interface, and you can map this to software, to any type of asset. We have extended this to also include variability, including the connection of the variability to these assets in our tool PTC Integrity Asset Library. So in fact, you can now publish variable components, and these variable components can be reused in a model-in-model concept. So I'm publishing my component with all the options which exist, and someone who is reusing this component will get exactly the variability included and can make some decisions in this area. Okay.
All right. So meanwhile, some questions came in.
Yeah.
So there's a first one from Steve Minter, who asked, can you please make this presentation available to the attendees on this call? For sure we can. So I just switched to the next question because there's some more. Another one asks, can this directly interact with a real machine or system? So I think it's about real-time capabilities of a system model.
Yeah, we have done so with using ThingWorx. Our model can directly interact with ThingWorx in multiple areas. We can generate device code from different languages. So there is also the software architecture link. But of course, if you have something which interacts here. We could also connect this to our IoT in the loop SiSim simulations. We have done an example for a street scooter. We are currently developing this with the successor of street scooter called Ego as an example to say, well, we have a simulation, but we need to directly interlink this with real systems in order to have the possibility to validate what we have modeled, for instance, in behavior and so on. So yes, it is possible, and we will have something, for instance, available for our LiveWorks presentation in June, where you can see this live.
Yeah, that sounds really interesting, because AVL as well is afflicted with real-time systems, and this is quite an interesting topic. Thank you for the hint. All right, so we got further questions. So John Person asks, for modular development, what is the relation between variability model and options and variants?
Yeah, we have a mapping between options and variants and our variability model. So things which are variable in the system structure, where you can use SysML blocks, block definition diagrams, and so on, and you have variability included. We can push this down into Windchill, for instance, where this variability is also, let's say, directly generated as options and variants. There is a slight difference in the way of describing generic parts within Windchill and a kind of overloaded product structure. But in general, you can map these two things together. So it is obvious that these variabilities have to be related to each other, and we can do so. Right now, we can do this in generating bill of material structures in Windchill, and from July on, in the new modular version, we will also be able to reuse things with options and variants into the model. So this is the way back from Windchill to modular.
Yeah, okay, thank you. So I think looking on the timetable, I would say I just pick up one last question now. This is from Andreas, who asks, how much does it take to develop such a knowledge base AVL is now using? So to be honest, of course, the knowledge base is still growing. So it took some time to establish the modular portfolio structure for our ITS systems. In fact, that depends, of course, on the size of a portfolio. So you cannot give a common language for that. We addressed around about 8,000 different products and options what are now classified into the structure, basically. But we are still continuing on completing the modeling of functionality and of interfaces there. But we're in a good way, and this is ongoing work that depends on our product development processes coming in, because we also implemented this methodology in our product development process, where part of quality assurance is also modeling the respective functionality and interfaces to be sure that they are tested. So in fact, this is an ongoing work, and I cannot give an answer in many years. But I think the most important aspect is, in fact, that you not just apply MBSE as it is, but rather think about how you can adopt MBSE to your specific needs. And you can use the capabilities of ergonomic profiling, using model templates and so on, to fitting MBSE as a methodology that fits well into your needs. And this is, of course, some pre-thinking effort and tryout effort, but I think PTC is a good partner to interact with, and they can give you tips and hints with their widespread experience in that area.
Christian, thank you very much indeed. Andreas, thank you too. There are still a couple of questions. Vishal's got one, which perhaps he can address to Andreas on the via the email that's on the end slide there. And also we have a question from an anonymous viewer about signal processing packages. sir or madam, perhaps you could direct your question to Andreas to that email address on the final screen. Any other points or issues you want to raise about the webinar, about the content, again, please address them either to Andreas, or if it's about the webinar itself and the processes of signing up, etc., please address it to my colleague, Fred Tung. That is indeed all we have time for today. I'm really grateful to Andreas and Christian for their time this morning, and thank you so much for attending. The contact details I've just mentioned. Over the next few days, Steve Minter asked if this recording webinar was going to be made available. Yes, of course it is. We'll be forwarding a recording of the webinar to all attendees. It will also be available on the manufacturer website and, of course, on PTC's website, which is www.ptc.com. That's all from us today, from both Andreas and Christian, and from me, Nick Peters, and the whole manufacturer team. Thank you so much for joining us. Goodbye to you.